quantum gravity sensor at MIT may have detected something that scientists can't explain. For a brief moment,
the moment gravity vanished, MIT's quantum void event gravity is a force we take for granted. Every step we take, every object we drop, every planet orbiting its star, all governed by an invisible pull we accept as unshakable. But what if gravity itself wasn't as constant as we believed? What if, even for a fleeting moment, it could vanish, fluctuate, or behave in ways that defy our most trusted theories? This is not science fiction. This is what researchers at MIT may have observed during a millisecond-long anomaly that is now being called a quantum void event. At the cutting edge of physics, the world is beginning to explore a radical idea that space and time themselves might not be fundamental. Traditional physics treats space and time as a fixed stage upon which all matter and energy interact. Newton saw it as absolute, Einstein showed it could bend. But a growing number of scientists now propose that both space and time emerge from something deeper. A network of quantum entanglements, microscopic pieces of reality so small that their interactions give rise to the dimensions we experience. In other words, what we perceive as the fabric of reality may be just a surface, a projection of an underlying quantum world. This is where quantum gravity sensors come into play. At MIT, researchers have been developing instruments capable of measuring gravity with unprecedented precision. So sensitive that they can detect minuscule changes equivalent to the weight of a single person standing underground, several meters away. These sensors operate at the frontier of experimental physics, combining laser-cooled atoms, torsional pendulums, and atom interferometry to probe gravity on scales never before achievable. In essence, they are designed to see the invisible, to detect the subtlest ripples and distortions in space-time. During routine experiments, something extraordinary occurred. For a mere 3 milliseconds, the sensor recorded a sharp, sudden drop in gravitational force, a near-zero reading that has no explanation in conventional physics or geology. Imagine monitoring the smooth, predictable pull of Earth when suddenly the signal plummets and then immediately returns to normal. It wasn't noise. It wasn't an equipment glitch. It was a distinct, clean dropout, an event that could suggest a momentary void in gravity itself. To understand the magnitude of this, we need to examine the instruments themselves. The MIT sensor uses ultra-cold atoms, cooled to just above absolute zero, colder than the emptiest parts of space. These atoms fall freely inside vacuum chambers while lasers split and recombine their quantum wave functions in a process called atom interferometry. Picture thousands of tiny quantum clocks falling simultaneously. If gravity shifts even slightly, the atoms drift out of sync, producing interference patterns that reveal the changes. This technique allows researchers to detect variations in gravitational pull with precision measured in parts per billion, an extraordinary leap beyond any traditional gravimeter. During the void event, these interference patterns behaved in ways that have never been observed. Instead of the gradual deviations caused by known underground structures, such as caves or tunnels, the readings showed a sudden absence of gravitational influence, as if the local fabric of spacetime had flickered. In contrast, typical geological anomalies, like an air pocket beneath limestone or a collapsed mine, would still exert measurable gravity due to surrounding rock and debris. This anomaly, however, was sharp, instantaneous, and clean, suggesting something far beyond conventional explanations. Scientists immediately began considering potential causes. The first possibility is mundane, a geophysical phenomenon. Could an underground collapse, void, or air pocket temporarily alter local gravity? While theoretically plausible, the precision of the measurement and the abruptness of the signal challenge this idea. Ordinary geological events leave residual gravitational signatures, small but detectable. Nothing in existing surveys or satellite data supports a hidden void of sufficient magnitude at the MIT site. The second possibility ventures into the cosmic and exotic dark matter. Dark matter constitutes roughly 27% of the universe and interacts primarily through gravity, remaining invisible to conventional detection methods. Some cosmological models suggest that dark matter may not be evenly distributed but could form transient clusters or pockets. Could this sensor have detected a fleeting interaction with a localized concentration of dark matter passing through ordinary space? This is speculative, but not outside the realm of possibility, and if confirmed would mark the first direct laboratory-scale detection of dark matter interacting with our world. The third and most radical possibility involves quantum vacuum instability. Even what we consider empty space is teeming with virtual particles appearing and disappearing in accordance with quantum mechanics. Under certain extreme conditions, these fluctuations could generate transient regions where the fundamental forces behave differently. The MIT void event could represent one such fleeting bubble, a microscopic lapse in the quantum structure of spacetime itself. This interpretation, if verified, would have profound implications, suggesting that the very architecture of reality is flexible and dynamic, rather than immutable. This brings us to the theoretical stakes. For over a century, Einstein's general relativity has provided an elegant description of gravity as the curvature of spacetime. Yet, while it accurately predicts the motion of planets, stars, and galaxies, general relativity does not reconcile with quantum mechanics, which governs subatomic particles. Physicists have long searched for a theory of quantum gravity, a framework that unites these two pillars. The MIT anomaly could represent the first experimental clue in that search, a laboratory-scale glimpse at the quantum behavior of gravity. Expert reactions are cautious but intrigued. Some theoretical physicists suggest the void event might hint at granularity in spacetime, consistent with loop quantum gravity models where space is not continuous but composed of discrete chunks at the Planck scale. Others consider it a potential signature of exotic matter or a dark sector influence previously undetected on Earth. What makes the event compelling is its clarity. Unlike many experimental anomalies, the signal was abrupt, well documented, and produced by instruments designed to eliminate environmental noise, vibration, and thermal fluctuations. The implications extend beyond pure physics. Quantum gravity sensors have enormous potential applications in industry, geology, and defense. DARPA, NASA, and other agencies are investing heavily in these technologies because they can map underground structures, detect tunnels, locate mineral deposits, and even track submarines, all without relying on conventional detection methods. A breakthrough in understanding quantum gravity, validated by events like MIT's void detection, could revolutionize technology from infrastructure planning to national security. Historically, anomalies have served as catalysts for discovery. The Pioneer anomaly initially puzzled scientists until thermal forces explained the deviation. Faster than light neutrinos shocked the physics community, only to be traced to a loose cable. Some phenomena, like the Tunguska event, remain unexplained, keeping scientists vigilant. MIT's void event, however, is distinct. It is measured with extreme precision and produced by equipment explicitly designed to probe gravity. If verified, it represents more than a puzzle. It could mark a fundamental gap in our understanding of nature. The scientific approach requires caution. Extraordinary claims demand extraordinary evidence. Researchers are now conducting repeated measurements, testing instruments, and analyzing environmental conditions to rule out conventional explanations. Multiple independent verifications will be essential to confirm whether this was a genuine void event, a fluctuation in dark matter, a quantum vacuum phenomenon, or simply a heretofore unknown geophysical process. Meanwhile, the broader implications are staggering. If gravity can fluctuate, even momentarily, our assumptions about the stability of spacetime, the predictability of physical laws, and the nature of reality itself come into question. Technologies like the MIT quantum sensor are only the beginning. Upcoming satellite missions, portable quantum gravimeters, and ultra-precise atomic clocks will allow humanity to measure the invisible with unprecedented detail, uncovering features of Earth and the universe previously hidden from view. The MIT Void event, fleeting as it was, represents a potential turning point in physics. It challenges assumptions, stimulates theoretical exploration, and bridges the gap between experimental ingenuity and the deepest questions of existence. While verification is ongoing, the discovery underscores the value of pushing instrumentation to its limits. Every advancement in precision sensing brings humanity closer to observing the hidden layers of reality. And sometimes, even a 3-millisecond event can illuminate truths far larger than the moment itself. MIT's potential void event forces us to ask, what if our universe is not as solid, consistent, and predictable as we imagine? What if spacetime, matter, and gravity are emergent phenomena, subject to fluctuation, instability, or unseen interactions? And what if, through quantum sensors, we are finally able to witness the fleeting moments where reality itself bends, folds, or disappears before snapping back into place? This is the frontier of modern physics, where theory, instrumentation, and imagination collide, and where each unexplained anomaly may carry the seeds of a revolutionary understanding of the universe. The science, the experts, and the quantum puzzle. To fully appreciate what MIT's potential void event might mean, we need to understand not just the instruments, but the science behind them and the theoretical stakes at play. At first glance, a 3-millisecond anomaly in a gravity reading might seem insignificant, a blip, a fleeting error in a sea of data. But in the world of quantum physics, even the tiniest anomaly can point to a reality-altering discovery. Every major leap in science, from Newton's laws to Einstein's relativity, began with something that did not fit the current understanding. Gravity, for instance, has always been mysterious. Newton described it as a force pulling objects toward each other, a mathematical law that worked brilliantly for centuries. Then Einstein revolutionized our understanding, showing that gravity is not a force but the curvature of spacetime caused by mass and energy. Planets orbit stars not because they are pulled by invisible strings, but because they follow the bends and curves in the fabric of spacetime. For decades, general relativity has been the bedrock of modern physics, predicting everything from black holes to gravitational waves with astonishing precision. Yet, general relativity has one major limitation: it does not reconcile with quantum mechanics. While general relativity governs the large-scale universe, stars, galaxies, black holes, quantum mechanics governs the microscopic world of atoms and subatomic particles. The two frameworks work beautifully on their own, but clash when we try to combine them. How does gravity behave at the quantum scale? Does spacetime itself become discrete, grainy, or fluctuating? Until now, such questions were purely theoretical because we lacked instruments capable of probing gravity at these extreme scales. This is where the MIT quantum gravity sensor comes in. Unlike conventional gravimeters, which can detect broad changes in gravity over large distances or masses, quantum gravity sensors operate at the atomic scale. By cooling clouds of atoms to near absolute zero, researchers slow their motion to a virtual standstill. These atoms, suspended in vacuum chambers, act as ultra-precise quantum probes. When they fall freely, lasers split and recombine their wave functions, creating interference patterns. Any fluctuation in gravity alters these patterns, revealing minute changes in the gravitational field with unprecedented precision. During the void event, the readings were unlike anything observed before. The sensor detected a sudden, almost complete drop in gravitational influence for 3 milliseconds. Unlike a gradual shift caused by underground voids, caves, or mineral deposits, the drop was sharp, clean, and isolated, suggesting a phenomenon beyond ordinary geology. To put it simply, the sensor seemed to measure a temporary absence of gravity, as if a tiny section of spacetime itself had disappeared and then reappeared instantly. Scientists immediately began theorizing. The first possibility, a geological explanation, seemed the simplest. Could the sensor have detected a previously unknown cavity, collapsed mine, or underground air pocket? While such anomalies can exist, they rarely produce perfect voids in gravitational readings. Material surrounding these spaces, even dust and rubble, still exerts measurable gravity. The abruptness of the MIT reading makes a purely geological cause unlikely, though not impossible. The second hypothesis is far more exotic: dark matter interactions. Dark matter, an invisible form of matter constituting roughly 27% of the universe, interacts primarily through gravity. It does not emit, absorb, or reflect light, which is why it has eluded detection for decades. Some models suggest dark matter could clump locally, forming dense pockets that create temporary gravitational distortions as they pass through ordinary matter. Could MIT's void event represent the first laboratory-scale observation of such a phenomenon? If so, it would be groundbreaking. The first direct evidence of dark matter interacting with our observable universe in a measurable way. The third and most radical explanation involves quantum vacuum fluctuations. At the quantum level, empty space is never truly empty. Virtual particles constantly appear and vanish, forming a restless background known as the quantum vacuum. Under certain conditions, these fluctuations could produce transient regions where gravity or other fundamental forces behave differently. In theory, this could create short-lived bubbles, where gravity effectively disappears or is altered, matching the behavior recorded during the MIT event. If confirmed, this would be the first experimental observation of quantum effects in gravity, a long-sought goal in physics known as quantum gravity. The implications of such a discovery are profound. If gravity is not as constant as we thought, it forces a reevaluation of everything from black hole dynamics to the evolution of the universe itself. It could mean that spacetime is not continuous, but granular, composed of discrete units at the Planck scale. It might imply that our understanding of cosmology, dark matter, and even the origin of the universe is incomplete. For decades, physicists have speculated about these possibilities in mathematical models. But until now, there has been no experimental evidence at laboratory scales to support them. Leading experts in quantum physics have weighed in cautiously. Makiaku, a theoretical physicist specializing in unified field theories, suggests the void event could represent the first laboratory-scale evidence of where Einstein's general relativity begins to break down. For over a century, scientists have searched for places where the curvature of spacetime cannot be explained by existing models. A 3-millisecond disappearance of gravity, measured by instruments with extreme sensitivity, fits the profile of such a phenomenon. Carlo Rowley, a pioneer of loop quantum gravity, interprets the event differently. His work suggests that spacetime itself is not smooth but composed of discrete units, like a lattice. The void event might be a manifestation of this granular structure, revealing the atoms of spacetime in real time. If so, the MIT reading could be the first glimpse into a deeper layer of reality, one that defies classical intuition. O.V. Loeb, a Harvard researcher specializing in anomalous astronomical phenomena, adds another perspective. He considers that the event might reflect exotic matter interactions, possibly even a previously unknown type of subatomic particle or energy field. While speculative, this view underscores the potential for entirely new physics to emerge from what appears at first to be a simple anomaly. What makes the MIT void event particularly compelling is the quality and clarity of the data. Unlike many reported anomalies, which are often noisy, inconsistent, or contaminated by environmental factors, this signal was recorded under controlled laboratory conditions using equipment specifically designed to eliminate interference. The ultra-cold atom cloud, isolated from vibrations, temperature fluctuations, and electromagnetic noise, provided a clean measurement that cannot easily be dismissed as experimental error. The historical context of scientific anomalies provides perspective. Consider the pioneer anomaly of the 1980s, when spacecraft slowed unexpectedly during deep space travel, confounding scientists. Years of study revealed it was due to heat radiation, or the 2011 faster-than-light neutrino incident at CERN, later traced to a loose cable. In both cases, the anomalies spurred investigation, rigorous testing, and improvements in instrumentation. But sometimes anomalies are more than technical glitches. Sometimes they reveal new physics. The Tunguska event in 1908, an explosion flattening 80 million trees over Siberia, still lacks a complete explanation, reminding us that nature can defy easy categorization. MIT's void event sits at this intersection. It is measured, verified, and extraordinary. It challenges assumptions about the constancy of gravity, the structure of space-time, and the completeness of our physical laws. If replicated, it could provide a rare experimental window into the interface between quantum mechanics and general relativity, a frontier that has eluded physicists for generations. Beyond pure science, the implications of quantum gravity anomalies are strategic and technological. Governments have been investing in quantum gravity sensing because it provides capabilities far beyond traditional surveillance or mapping. DARPA, NASA, and other defense agencies recognize that such instruments can detect underground structures, hidden tunnels, or even submarines with unprecedented accuracy. If MIT's sensors are capable of detecting anomalies in gravity itself, the potential applications extend from geophysics to national security, making this not just a scientific milestone, but a potential strategic breakthrough. In practical terms, this technology could transform the way we interact with our planet. Imagine mapping subterranean water sources without drilling, detecting hidden geological faults before earthquakes, or uncovering mineral deposits deep beneath solid rock. Beyond Earth, quantum gravity sensors could probe planetary interiors, analyze moons, or detect subtle gravitational interactions in space, giving scientists and engineers tools never before imagined. The scientific rigor surrounding the event is critical. Extraordinary claims demand extraordinary evidence. Researchers are conducting repeated measurements, running parallel experiments, and isolating every possible environmental variable. They are also collaborating with other institutions worldwide to replicate the anomaly independently. This methodical approach is essential, ensuring that what might appear to be a groundbreaking discovery is not, in fact, a transient artifact of instrumentation. Even with caution, the event sparks imagination. A temporary disappearance of gravity, however brief, challenges our perception of reality itself. Could space-time fluctuate like a quantum field? Could matter interact with unseen forces? Could dark matter reveal itself in localized, momentary ways? Each of these questions pushes the boundaries of our understanding and invites new theoretical explorations. MIT's void event also highlights the convergence of experimental innovation and theoretical ambition. The sensors themselves represent decades of advancement in atomic physics, laser technology, cryogenics, and quantum measurement. Theories of quantum gravity, dark matter, and vacuum fluctuations provide a conceptual framework to interpret these measurements. Together, experiment and theory create a feedback loop. Instruments test predictions, and anomalies refine theory. The void event is the perfect example of this synergy. Finally, the event reminds us that the universe may be far stranger than our everyday experience suggests. Gravity, something so familiar we rarely question it, might not be constant. Space and time, dimensions we take for granted, might emerge from a deeper quantum web. And in laboratories like MIT, instruments sensitive enough to detect a millisecond fluctuation are beginning to reveal these hidden layers. The void event, brief as it was, could represent the first real glimpse of this hidden reality, challenging our understanding and inspiring the next generation of physics. Implications, theories, and the frontier of discovery. The potential implications of MIT's void event extend far beyond laboratory curiosity. What we are witnessing could represent the very beginning of a new chapter in physics. A chapter where the familiar laws of gravity, as described by Newton and Einstein, may not tell the full story. To grasp the gravity of this discovery, it's essential to explore its scientific, philosophical, and practical ramifications. First, consider the scientific ramifications. If this anomaly is confirmed as a genuine effect, and not a glitch or mundane geological event, it may provide the first experimental evidence of quantum gravity. For decades, physicists have sought a theory that unites general relativity with quantum mechanics. Known as the Holy Grail of modern physics, quantum gravity promises to explain how space-time behaves at the smallest scales and how the universe functions under extreme conditions, such as the singularities inside black holes. MIT's void event, lasting mere milliseconds, could be the first glimpse of gravity behaving differently at quantum scales. Imagine that for 3 milliseconds, the sensor recorded a localized weakening or even temporary disappearance of gravity. At first, this seems almost surreal. Gravity is the force that holds planets in orbit, binds galaxies together, and anchors our feet to the ground. To imagine it flickering, even briefly, challenges every intuition we hold about the universe. Yet quantum mechanics has taught us that the micro-world often defies intuition. Particles can exist in superposition, entangle over vast distances, and tunnel through barriers they seemingly cannot cross. Could gravity, at its most fundamental level, behave in similarly surprising ways? The void event suggests it might. To explore this further, let's examine the leading theoretical explanations. One hypothesis involves quantum vacuum fluctuations. In quantum field theory, the vacuum is far from empty. It is a seething landscape of virtual particles constantly appearing and disappearing. Under certain conditions, these fluctuations could create temporary regions where the fundamental forces behave differently, including gravity. Such a quantum void would be extraordinarily brief and localized, exactly like the 3-millisecond anomaly observed at MIT. If confirmed, this would be the first time humans had directly measured a quantum vacuum effect on gravity, a discovery that could reshape physics textbooks worldwide. Another compelling explanation involves dark matter interactions. Dark matter is one of the most mysterious substances in the cosmos,